So now that we know, what Euler's method is, kind of, and why we would want to have it, we're going to go through the steps that you actually use to implement Euler's method. So we're going to go over the steps to use Euler's method, and I'm going to actually write out like the way the problem should be given to you first. So it's going to be that we're given some initial value problem. dy dx equal to f of xy. So like direction fields, you can have dependence on x in the differential equation, and you need to be given an initial condition to start from. And the way we're going to use Euler's method is we're going to first start at the point x0, y0 that we read off from our initial condition right there. And then at that point, we will compute f of x0, y0. So we'll plug that point into the derivative. This is us getting that slope. And then once we have that value, we can start updating our points so we can move forward in that graph. We're going to take x1 to be x0 plus h, and y1 to be y0 plus h. H times f of x0, y0. And h is what's called the step size. It's how quickly we move along the x-axis when we're trying to follow those arrows. So you can think about like, if I had to follow these arrows the way they're written, I have to follow this one for that long, and then I can follow the next one until I reach a new arrow. If I drew a lot of really small arrows, I could hop between them with smaller steps. So just a note here, you're going to need step size, which we've denoted here as h. You're going to have to specify it, or sometimes it's given in the problem. And then eventually we're also going to have to decide when to stop. That's step 4, is we're actually just going to repeat this process until you reach that point where you want to stop. And we're just going to call that our desired x value. So if I wanted to know my solution here, I would have to keep going until I reach that x value, and I would find that value on the green line. And so we've got time. Let's go ahead and run our first example here. I'm pretty bad about this in the videos, but anytime you need to pause to catch up with writing, please go ahead. I don't like to add a lot of white space just for people who are trying to get through them quickly, but if you're writing along and not using the skeleton notes, it can be quite a lot to write at once. So hit pause anytime you need to, and I'm going to go ahead with the example. So we want to solve this differential equation. Y prime is 0.1 square root y plus 0.4 times x squared. And we want to start from the initial condition y of 2 equal to 4. That means we start with x equals 2, y equals 4. And using step size 0.1, we just want to go ahead and compute y at the value 2.2. So putting this all in the same terms as our steps here, we've got that f of xy is that 0.1 root y plus 0.4 x squared. It's the thing that's equal to the derivative in our original problem. The point x0, y0 that we need to start from comes from our initial conditions. That's right here. Our initial x is 2, our initial y is 4. So x0, y0 is 2, 4. Our step size h is given to us in the problem, and for a lot of your assignments, you'll be given that. So we're told to use step size h equals 0.1, and then we want to reach this value y of 2.2, so we need to keep going until we reach x equal 2.2. And with that, we can go ahead and start trying to follow these steps. So we start at x0 equals 2, y0 equals 4. So that's our start at x0, y0. And here, we're going to have to evaluate f of x0, y0. So that's f of 2, 4, which is going to be 0.1 root y is 4, plus 0.4 x squared is 2 squared. Which I didn't write that value here. But I did write it down when I calculated in y1, so we'll just keep going for now. So when I get to my update point, what I want to do is I want to say, okay, x1 is x0 plus h. So that's going to be giving me 2 plus 0.1. That's my x0, that's my h, which is 2.1. And then y1, we're going to follow this formula. It's y0, which was 4, plus h, which was 0.1, times f, which I calculated right there, 0.1 root 4 plus 0.4 times 2 squared. It's a bad squared. So that was my y0 plus h times f of x0, y0. And I plugged that into a calculator and got that it is 4.18. You will need a calculator to do these problems. I'm only at x equals 2.1, so I have to keep going. I repeat until I reach my desired x value, and that's 2.2. So if I do the same thing, x2 is going to be what was my previous value. So last time I had 2.1, so I go ahead and put that in. And then I add on the step I'm taking, 0.1. So I plug in x1 plus h. And that's going to give me 2.2 now, which is great. That's the x value I'm going to. So as soon as I update my y, I'm done. So y2 is going to be the previous y value, 4.18, plus that step, 0.1, times f. And this is where it starts to get kind of tricky because you have to plug in these really gross numbers to this really gross function. But it's 0.1 times square root y. So right now my y is 4.18. I'm going to put that in there. Plus 0.4 times my current x value, which was 2.1. Squared. So this is y1 plus h times f of x1, y1. And that was 4.38-ish. I rounded off. when I plugged it into a calculator. And so at this point, I would be done with my problem. I would say, great, you asked me to approximate y of 2.2. It's about 4.38. And there's a lot to be careful about in this type of problem, and I'm going to actually go through them step by step to give you things to sort of watch out for when you're doing this. But I do want to highlight, while we're still thinking about the problem, that step 4, repeat, is really easy to forget. That means you need to be continually updating all your values. So don't just go back and plug in x0, y0 a bunch of times. When I say repeat, I really mean like when we go back to 1, now we're starting at x1, y1. And we do everything that way. And then if I had to keep going, then I would start at x2, y2. And keep going that way. Just be careful you don't miss that like nuance of this method, and then you should be good.